Hi, I'm Chris Brown, and this is the fifth module in a series on an introduction to axiomatic design that's part of a larger course, Axiomatic Design of Manufacturing Processes, here at WPI. I'm a professor in the Mechanical Engineering Department. So for the next 15 to 20 minutes, we're going to be talking about decomposition and decomposition rules. In other words, how do we come up with a good decomposition? What does it look like? How can we tell if it's good? So decomposition rules. It turns out this is an important step in doing a design. The design and the decomposition is top-down. We start with the general, the broadest, most abstract needs, and then break it down into little workable chunks. And you can see that the way we're intended to do that is so that we're taking the upper level and just slicing this into smaller and smaller pieces, not adding anything and not losing anything. Anyway, so this is key to a good decomposition. So it helps to break work into little independent chunks. There we go. So that's supposed to be funny. Okay. Objectives. Understand the decomposition process. And along with doing this, we're going to be developing the design solution. And we're going to work across domains and down the hierarchy. And so this is how to build a decomp. So we're going to use the term decomp as a noun, as opposed to decomposition, which is can be used as a verb, or if we're being very specific about it, we'll call it a decomposition process, in which case it's a process that produces the decomp. So first let's note that the ability to decompose problems into smaller elements is one of the most important parts in solving large and complex problems. And those that go beyond an obvious solution. So we have some experience with that, certainly, but do we know how to do it systematically and so that we come up with a good, useful result? So that's what we're going to be looking at. And after we're through decomposing the solution or decomposing the problem until the solution is obvious, then it needs to be integrated into the complete solution. All right, so for this lecture we're going to start the development with the FRs. And so we're assuming that the FRs have a good basis in the customer needs and are appropriately in the value chain that the customer needs established. And then developing the CNs is going to be delivered in a later lecture, and we'll concentrate just on that aspect of it. The FRs, as we talked about in the last module, establish the function, the design intent, and they are essential to innovation and a good design. So for this lecture, the discussion is limited to the FRs, DPs, and DPs. The PVs will be considered later. So the structure of the design is developed during the decomposition process, the specific details of the structure. The process is one of zigzagging, going between the domains, and then from functional to physical, and then down the abstraction ladder from general or conceptual to the bottom level, which we call the leaf level, the nuts and bolts, and some people call it the nitty-gritty part of the design. And at that level, and how do we know when we've decomposed far enough? Then the solution becomes obvious. So here's the zigzagging decomposition. FR0 is the top intent, it's the top level, and so that is the first thing that we need to sort of establish and get consensus on with the team that we're working with. So FR0. So once we have FR0, then the first step is to get DP0, which might be a manufacturing system, or it might actually be sourcing the part. But I'm sorry, that would be a PV0. The dP0 is going to be something physical. So that's the physical set that satisfies the FR, or fulfills the FR. All right, so we have the dP0. So the dP0 might be something like a hydraulic system or a pneumatic system, and this is going to provide essentially a constraint on the subsequent decomposition. Whatever we decide for a physical element at a higher level, this constrains the kinds of functions we're going to be looking for at the lower level. So once we've decided what dP0 is, then we can further decompose FR0 in the context of what dP0 is, and we get FR1 and FR2. So now that we've got FR1 and FR2, and they should be somehow appropriate decompositions of FR0, and we'll study that more in a moment, then those will be used to select dP1 and dP2, such that dP1 fulfills FR1 and dP2 fulfills FR2 in a logical kind of way. So now we've begun two branches. It could be any number of branches at this level, level 1. So, but 2 is easier to illustrate, and 1, as we'll see, will be inappropriate. So let's follow these branches down now. So from the DPs at this level, we then go down and see, all right, so what are the FRs at the next level? And just arbitrarily, I've chosen FR1 will be decomposed into 3 children, and FR2 will be composed into 2 children, and we can see how they're numbered. So they each have a unique number that traces which branch it's in and which level it's in. Then these FRs, from these FRs, we're looking for DP1 and 1.2 and 1.3, which somehow got distorted a little bit. I apologize for that, but you can see how it goes. So the DP numbers correspond exactly to the FR numbers and are intended, as we said, to fulfill those FRs. So, and each FR gets its own DP. All right, so there's the zigzagging decomposition, and those are the steps it goes through. Now, at each level there, we're going to be checking for compliance, and we'll see how to do that in a later one. Checking for compliance with Axiom 1, Axiom 2, and violation of the constraints as we select the DPs to satisfy the FRs, but we'll talk more about that later. So at each level in each branch, let's concentrate on the FRs for a moment, because they're going to be developed first, based on the CNs, of course, and what the FR parents are as we get down in the hierarchy. Now this is an important concept for any kind of decomposition, and that is CME-min. So this is an acronym for collectively exhaustive, mutually exclusive, minimum number. So this is kind of a mantra that we want to be saying as we decompose the FRs. Let's see what this means. Collectively exhaustive. Did you think of everything? That's the CE. So we want to make sure that we've thought of everything. It is the engineer's job to think of everything that could result in failure and address those, or everything that could hurt the operator and address those, or everything that needs to be done, and make sure that all of those things are done in that design. Now, the engineer does their job. The planes don't crash, the cars don't crash, the bridges stay up. So in a certain sense, engineers only get attention when they don't do their job, or they didn't think of everything. Collectively exhaustive. So in my mind that comes first. Mutually exclusive. Make sure you thought of everything. Mutually exclusive. Is there redundancy? Is there overlap? If so, then simplify. We want these things to be, we don't want to satisfy 2 things. We want the FRs to be all independent, so they have to be completely mutually exclusive. And then the last one is minimum number. Only what is necessary. Simplify. There are no points for coming up with this design is even better than intended. Now let's go back to your intents and intend the right thing that satisfies the market, and then develop the FRs on that. All right, so here's another way of saying C, me, min. The sum of the children have to equal the parent. Now we'll be using this a lot. What this says is the elements at the next lower level of the decomposition are children of the parents at the higher level, and together they have to be equivalent to the parent, because all we're doing is taking the upper level abstract general solution and dividing that into different parts. So at each level of hierarchy, sum of the children equals the parents. And this helps to assure the C, me, min. Now here's the way, if we look at it, for example, in set theory. So we've got a larger sort of parent set that will be divided up into some number of elements in a child set. And the parent set S is exactly equal to the union of the children sets. So all we're doing is just adding those together. And the intersection of any of the children should be 0. So there is no intersection. So that means, if that's true, the decomposition is collectively exhaustive and mutually exclusive, and also the minimum number, or could be construed that way. All right, there should be no single child decompositions. Why? All parents must have at least 2 siblings. Otherwise, it has not been decomposed. If you can only think of one child, then probably one of 2 things are true. Maybe all you did in that child was to restate the parent. Maybe you added some more detail. All right, then move the detail up and put it in the parent. So sometimes when you come up with a one-child decomposition, as I said, it's just restating the parent. But maybe you're missing a child. And so that means you were not collectively exhaustive. So you want to be very careful about that. Go back and say, did we completely decompose it? One of the ways you can look for a missing child is in the theme, and we're going to talk about that, and in the language of the parent. And we'll talk more about that later too. All right, so symbolically, mutually exclusive means there's no overlap. FR1, FR2, FR3 are not overlapping. And so these are mutually exclusive. And so if they're not mutually exclusive, then that means I change something and 2 FRs change. And that's not maintaining the independence of the functional elements. So that violates axiom 1. So when we talk about maintaining the independence, this is one of the places where we have to maintain it. This is a key place. As we define the FR children, we have to make sure there's no overlap, because otherwise we've got 2 FRs that are clearly linked, and we won't be able to change one without changing the other, and we've lost the independence. So here's another sort of representation of what we looked at before. When we decompose the space for function 1, all we're doing is drawing lines and delineating parts of this to be 1.1, 1.2, 1.3, and 1.4. And if we've done that correctly, the sum of the children equals the parent. But how can we be sure that we've done that? Now here's something else too, the orthogonality. So that's what we're talking about. If there's overlap, they're not orthogonal. Now, a free body diagram generally is developed, lots of times developed in a Cartesian space. So we've got fx, fy, fz, and these axes are all at 90 degrees or orthogonal. And so when we have, say, a vector like f represented here, the red vector f, we want to decompose that into fx, fy, fz. And we have these 3 independent vectors that then signify somehow the resultant vector f. So, because the axes are orthogonal, there is no projection of fx, for example, in the zy plane besides a little point at the origin. Same for Fy in terms of Fz and Fx. So this is orthogonality. And so I can change, if the Fx component changes, it does not change the Fz and Fy automatically. So a couple things on the FR formulation. Getting this right is critical. So we want to make sure we translate these CNs into engineering terms. We want to make sure that they are capable of having performance tolerances. Now, lots of times we get into functions or performance that we're not used to quantifying, and that will be part of the exercises we take on later. It's key that we learn how to do that. But and we also want to be able to put performance or functional tolerances on the FRs. Now here's an important one, the third bullet there. The FRs need to be created in a solution-neutral environment. Don't jump the gun on the DPs. It's a time to dream in color. What do you really want in the FR? Keep in mind that formulating good FRs is going to take time and adds value to the design, so it's time well spent as you try to formulate those generally. Now, so as I said, don't jump the gun on the FRs. This is some of the stuff we'll cover later too. In more detail about how to tell. Don't telegraph the design parameter in the FR. Try to state it so that any DP might be acceptable. All right. What's one of the problems you have? Often the FR, getting the quest to find or trying to get the FRs appropriate, is often overlooked when we try to find the solution. So the DP is essentially the design solution. So we get sort of fixated on that and then forget to carefully define the functions that we're trying to fulfill with the different solutions. So as I'm fond of saying, the FR tells you where you want to go, and if you don't know where you're going, you don't know when you've arrived. So if the FR defines the tolerances and so forth, and you can meet all of those, then you're done. So high-level FRs and DPs require care. So the FR0 defines the direction and sets a theme. So plan on investing some time in the top of the hierarchy. Now that might be something you're not used to doing, and when you're judged merely on the sort of time evaluation, the only thing that counts is when you get a CAD drawing done, then probably you're not spending enough time at the more general levels, the upper levels of the hierarchy, trying to see what kind of solution we're looking for to a particular problem, and putting some of that together. So we need to have the right theme, and it takes some time to do this, to get things stated well in words. Now we talked about how the upper level DPs constrain the lower levels. So once you've decided that it's like a hydraulic system or something, all of the FRs from there down will indicate hydraulics. And so it may be necessary to go back and revise some of the earlier lectures as well. All right, FRs. Begin with verbs, imperative and form. We've already said that. And here's some examples. Limit motion to the X direction, for example. This can be important on a machine tool. Transmit loads so that we get back to some sort of solid kind of reference inertial frame. Provide stability, for example. Create features, transform microstructures, apply force. These are all noun-verb pairs that are verb-noun pairs that could be used for FRs. Limit, transmit, provide, create, transform, apply are all verbs that apply to the FRs. So themes and decomposition. What does this do for us? Well, we can make sure that we're collectively exhaustive, because if we have some sort of theme, we can see, geez, did we get everything within this theme if it's stated and we understand it right? So sort of how do we know we thought of everything? Well, the then the next part is how do we know that we're keeping things distinct and we haven't overdone it, so it's mutually exclusive, collectively exhaustive. And then the minimum number, how do we know we don't have more than we need? So some of the themes that you can use in decomposition would be temporal. At what time does this thing have to operate? Spatial, where is it located in space? Energetic, in terms of how it's interacting with energy, or just a component. In other words, I have different portions of something. How do I know I've covered it all? And then there's always the handy thing, other. And so we can use that when we're doing a decomposition and sort of hedge our bets a little bit and say, well, here's one category, other, and then we can see if anything comes up that needs to be included in that. Appropriate children. It's so nice when children are appropriate. Children should be clear descendants of their parents. And so we have to recognize the right kinds of categories to know that the children are in the right branch or in the right family. So look at the wording of the parents. As you do the decomposition, use similar terms for the children. Getting more detailed is appropriate. And sometimes the FRs, you can just, from an FR, you can take the verb-noun pair and at one level decompose the verb and at the next level the noun, or vice versa. Here are some examples for generic DPs. And so we're looking for different kinds of systems generally, but anyway, so the DPs could be for a component or for a force device, or a device rather, method, module, mechanism. And so what we're doing here is we're taking whatever the noun was, or the verb was in the FR, and plugging that into the blank. And so in some ways, all we would have to, we might look at this and say all we really need to do is to be able to restate the FR for the DP. Well, this works well at a higher level, and we can show you some examples of that. But if the FR is to prevent somebody from slipping, and all you can do is come up with a system that prevents them slipping, then this could be an expensive sort of design, and it also doesn't seem to be adding anything. So at some level we have to stop just using general or generic DPs. But they can be useful for expediting progress at the higher levels, and then put in modifiers later. For example, a price, device. Anyway, so you could have a different kind of a more specific kind of device at a lower level. Is it going to be a pneumatic or a hydraulic device? Themes of mechanical design are often position, sort of load transmission, motion control. And let's take a look at an example here. Suppose our FR0 is to prevent something from exploding. Say like a battery that you don't want to have exploding in your cell phone or in your computer. So the theme could be energy, and we could say, well, let's prevent it from exploding due to chemical energy, let's prevent it exploding from electrical energy, and let's prevent it from exploding from thermal energy. So these are all different kinds of energy, and then pressure, so there would be energy stored in, say, a gas or something. So these are all different kinds of energy, and so we've selected an energy theme. Were there any kinds of energy that we missed that might be in a battery? Chemical, not so much mechanical, chemical, electrical, thermal, and air compression. So what is the minimum number? And this kind of misses. It's intended to circle FR4. So it turns out the only reason things explode is from a pressure differential. So that in this case we don't need the FRs for prevent explosion due to chemical, electrical, or thermal. The only thing we really need is to prevent an explosion due to pressure. And this leads us to a much better design solution, a much simpler design. So here's another decomposition theme, spatial versus energy for protecting people. So if the FR0 is to protect users from injury, we might say protected machine X, protected machine Y, protect from different energy types. And then, so does the decomposition really matter? Because at the low level, we have all kinds of, we have these different kinds of protective devices. So, so in general, these are going to be supplied to protect different sort of body components. All right, the zigzagging decomposition, we've seen that already. Here are some steps. Identify the customer needs, develop FR0 and DP0 consistent with the objectives and the customer needs. Develop the next level of the FRs with the higher DPs and the customer needs. Select the DPs corresponding to the FRs. Check developed FRs and selected DPs against Axiom 1 and Axiom 2 and the constraints. Modify and consider alternatives as necessary. To assure compliance with the axioms, go to the next level down or adjacent branch and start at 3 again. So, so these iterations are productive iterations since they're developing the decomposition, and the extent to which the decomposition is developed is a good measure of progress in design. We'll talk about that. So repeat that until the solution is obvious. So if we take a look at our criteria for evaluating, so FRs, imperative form, beginning with a verb. DPs does not contain a verb, it's a noun. Although it may contain sort of a present participle as opposed to a verb as the FR would have it. So is it a reasonable decomposition? Are the children derived appropriately by decomposing the parent? Each parent, of course, must have at least 2 children, as we discussed. And the FRs at each level must be the minimum list, completely fulfilling the parent and the customer's need, or the customer's need. And so this means that they need to be collectively exhaustive. The FRs need to be independent of each other, so that they can be mutually exclusive. Generally like to avoid conjunctions and try to look for a term that is encompassing, but if you do end up with a conjunction, then the decomposition of the next level is obvious. So thank you very much for your attention.